Okay, hello everyone. Our group will use the reproducibility laws to improving image classification. First is the introduction. We introduce a simple new idea, retrospective laws that utilize prior training experience in the form of DNA model states during training to guide weight updates and improve DNA training performance. We propose law 6 to ensure that the prediction at the particular training steps are more similar to the ground truth than the predictions from the previous steps. As training proceeds, minimizing these laws, along with the task-specific laws, encourages the network parameters to move towards the optimal parameter state by pushing the training into tire space around the optimum. The proposed retrospective laws is easy to implement, and we specifically show through the comprehensive set of experiments across domains and corresponding application studies that it works very well in input domains, multitask, as well as the network architectures. Figures show the illustration example of the use of retrospective laws in the simple cases of Linux training on the FMIS datasets, which results in significantly improved representations. The key contributions in our work can be summarized as follows. First is we propose a new, simple, easy to implement retrospective laws that is based on looking back at the practical of gradient descent and providing an earlier parameter state as guidance for further learning in section 3. Next is we exhaustively experiment across domains, images, as well as on the rest of the task, including classifications, few shorts, learning, and games, and consistently beat state-of-the-art models on benchmark datasets, with addition of this laws term during training. Third is we analyze and explain the intuition and the reasoning behind why it works, as well as the conduction of obligation studies to study the impact of various choices in section 5. We will best of our knowledge. This is the first such effort in its perspective, and our empirical studies shows consistent improvement and performance across tasks in our multiple trials, demonstrating potential for practical use in real-world application across domains. Okay, let me introduce the FMINIST dataset with retrospective laws. First, let me introduce FMINIST dataset. The size, the format, and the training set division of FashionMINIST are exactly the same as the original MINIST. 60,000 over 10,000 training and test database division, 28 multiple 28 grayscale image. You can directly use it and test the performance of your machine learning and deep learning algorithms without any code changes. The next is the models deal with the FMINIST. The first one is LeNet5. LeNet5 is a pioneering 7-level convolutional network that classifies digits was applied by several banks to recognize handwritten numbers on checks digitized in 32 multiple 32 pixel grayscale input images. The ability to process higher resolution images require larger and more convolutional layers, so this technique is constrained by availability of computing resources. The next is ResNet models. At the iOS VRC 2015, the so-called residual network neural network introduced novel articles with skip connection and features heavy batch normalizations. Such skip connection are also known as gated units or gated recurrent units, have a strong similarity to recent successful elements applied in RNNs. Thanks to this technique, they were able to train a neural network with 152 layers while still having lower complexity than VGGNet. It achieves a top 5 error rate of 3.57%, which beats human-level performance on this dataset. The next is the experiment and the results. For experiments on FMINIST, we use LeNet5, ResNet20, and ResNet50 architectures. Models in each experiment are trained to converge using the Adam optimizer with learning rate equals to 0.05 and the mini batch equals to 32, running over 200 epochs. Results in figure 1 to 3 shows that using the retrostatic loss results in a better and faster convergence with significant gains, especially on minute 5. And the blue line represents with retrospective loss, and the red line represents without retrospective loss. And the table shows the image classification results, the test error using retrospective loss on F-minute datasets. Next is the analysis. The first one, why there are significant gains, especially on NANET5. Reason the characteristic of NANET5 can be summarized as follows. The convolutional neural network uses 3 layers as a series, convolutional, pooling, and nonlinear. The second is using convolutional to extract spatial features. The third is using mapping to spatial mean subsample. Fourth, hyperbolic or S-shaped linearity. The fifth is the multiple layer neural network as a final classifier. The sixth, the sparse connection matrix between layers avoids large computational costs. For ResNet, when the deep neural network reaches a certain depth, the accuracy rate is close to saturation, and if it is continued to deepen, the accuracy rate will be reduced. This is called the degradation problem. And this problem is not caused by overfitting, nor is it caused by the vanishing gradients. So the representative loss can be improved, LANET better than ResNet. The second is why choose Adam optimizer, not SGD in our work. Reason is essentially Adam is an algorithm for gradient-based optimization of stochastic objective functions. It combines the advantages of 2 SGD extensions, root mean square propagation and adaptive gradient algorithms, and computes individual adaptive learning rates for different parameters. And the third, why choose parameters with learning rates equals to 0.05 and the mean batch of equals to 32. And from these pictures, we can show, I do the experiments with the representative loss and without the retrospective loss. And from the results in this picture, we can see the best training accuracy in our work is the batch size equal to 32 and the learning rate equals to 0.05. So that's why I choose these 2 parameters. That's all.
Hello everyone, my name is Martin. I will introduce some experiments on 2 data types to test the low loss function. In order to test the new loss function, we designed a series of image classification experiments on multiple benchmark datasets, including fashion list, SVHN, CSIT5910, and tele-image datasets. For each dataset, we use widely used architectures like ResNet and VGG to show the usefulness of the proposed loss. For experiments on SVHN, we use VGG11 and the ResNet 18 architectures. Models in each experiment are trained to convergence using the SGD optimizer. The learning rate is 0.01, momentum is 0.9, and the mini batch is 100. Every model will run over 200,000 steps. And for experiments in CSIT5910, we use VGG11 architecture. Models in each experiment are trained to convergence using the SGD optimizer. The learning rate is 0.1, running over 200 epochs. First, I will introduce SVHN dataset. SVHN, which means Street Warehouse Member dataset. This dataset is derived from Google Street Warehouse Member. It can be regarded as similar to MList. For example, the image is a small clipping number that contains an order of magnitude of tag bits, more than 600,000 digital images. The original dataset is some original unpurposed color images, as shown in the first figure. The downloaded dataset contains PNG images and the location information of the border. In the experiment, the numbers are cropped to the size of 32 multiply 32, as shown in the right figure. Then I will introduce VGG9. VGG means Visual Geometry Group. This network is characterized by its simplicity. Generally, VG16 and VG19 networks are more widely used, but in order to make the network as small as possible, we choose VGG11 network to do new experiments. Models in each experiment are trained to convergence using the SGG optimizer, which learning rate will be 0.1 running over 200 epochs. Then, in this slide, we can see the accuracy curve of VGG11 with the low loss. And like in this slide, we can see the accuracy curve of Resolite 18 with the low loss. From the experimental results of the above two models, we can see that using the low loss function, the model can achieve higher value accuracy in image classification experiments. For original VGG11, we can observe that from the 18th generation, the testing loss curve of the model does not decline, but starts to rise, which indicates that the model has entered the fading state and should not continue training. This is because the performance index I tested in early stopping is not valid loss, it is valid accuracy. Therefore, cannot end training in time when the loss of the model stops fully. So, when we compare the valid loss, we will only select the loss of 18 generations. From the experimental results, we can see that the change trend of the valid loss of the two models is roughly the same. The final result of the valid loss of model with low loss is smaller than that model with the origin one. When we compare the valid accuracy, in order to get the value of accuracy, we will choose the valid accuracy of 200 epochs. From the experimental results, we can see that the result change of the valid accuracy of the two models is still roughly the same. The final result of the valid accuracy of model with the low loss is larger than that of model with the cross-entropy loss. And the specific clues of the final results of all experiments are shown in the table in this slide. Finally, for the new experiment we designed, we carried out some analysis of the experimental results. The final result shows that using the new loss results in improvement in performance almost all through in training. However, in third experiment, after a few iterations of VGG11, the model began to overfit. In this case, the change of model loss is not enough to reflect the change between the old model and the new model. Therefore, compared with the large variance of network like Resolite 44, 36, and 110, the experiment mental effect of VG11 is not obvious. After that, we can use deeper network like VG15 or 19 for experiments. So that's all. Thank you.
I will introduce my code explanations. First, this part is to set up the parameters of the models. And the random seed is 42, and learning rate is 0.01, and batch size is 32, and epochs is 50, and the image size is 32, and the classes is 10. The next is the function for computing the accuracy of the prediction over the entire data loader. The next is the function for plotting training and validation losses. And this is the function of training step of the training loop. And next, the function for the validation step of the training loop. This part is the function of defining the entire training loop. And I will use the Group15 for the demonstration, and the other is the same as Group50 for different coding on the Group50. Maybe it's the Lanet 5 or ResNet 20. Okay, that's all.
Hello everyone. Now I will show you some details of the code for the image classification experiment. I will take the experimental code, which uses the VGG11 network on the CSIT dataset as an example. In this slide, we can see the most basic structure of VGG network. This network is characterized by its simplicity, using only 3 plus 3 conventional layers stacked on top of each other in increasing depth. Reducing value set is handled by max pooling. So here, I define the basic 3 multiply 3 small conventional network curve and max pooling unit. According to the structure of a VG11 network, I set 8 conventional layers and determine the dimensions of input and output metrics of each conventional layer. For the original VG network, according to the experimental plan, the learning rate is set as 0.1, and the loss function is cross entropy loss. The whole training will be conducted 200 epochs. Now, for the VG network, using the low loss function, the learning rate is still set at 0.1, and the basic loss function is cross entropy loss. Then I added the low loss function step. The low loss function uses the result of cross entropy loss function to further calculate loss. The specific principle can please refer to the previous content. So that's all. Thank you. If you want to know more about code details, please read the submit the code.